Welcome to the workshop. We want to take a look at an example of developing our integration techniques. So we've seen several techniques already, integration by parts, partial fractions, trigonometric integrals, trigonometric substitution. And we just want to now look at some integrals and say, all right, how do I approach this one? So I'm not looking at a specific technique here. I'm looking at trying to decide which technique to use. So let's take a look at an example here. So our first example is of the integral of theta times inverse secant theta d theta. For this example, we need to decide, first of all, what technique we want to use. So we might go through a list of questions that we have for ourselves on trying to decide what to do. So we start by saying, can we simplify anything? And in this case, the integral of theta times the inverse secant of theta, not really anything to simplify that. So we say, okay, is there an obvious substitution? Not really. At least I don't see one. If you see one, that's great, right? We all have our different strengths. So we want to focus on those as best as we can. But of course, not every integral is going to play into our strengths. All right, so no obvious substitution. So we say, all right, let's classify the integrand. Let's look at this piece right here. We ask ourselves, is it just trigonometric functions, or is it something that we recognize as just a trigonometric integral? So in this case, having theta times inverse secant, that's not what we're looking at, right? Trigonometric integrals refers to having powers of sine and cosine, or powers of tangent and secant. And we have inverse secant here. We don't have powers of secant. So that's not what we're looking at. Do we have a rational function to use partial fractions on? No, we don't. So we say to ourselves, all right, well, what about radicals? Do we see any trigonometric substitutions that would go on here, right? Are we looking at something that has the square root of a squared minus u squared, or one of the other two forms that would encourage trigonometric substitution? And of course, we don't see that here. So our last method, of course, is going to be that of integration by parts. And we ask ourselves, do we see something that looks like a polynomial times a transcendental function? And a transcendental function is anything that really doesn't work out to be represented by polynomials or rational expressions, this sort of thing. So the transcendental functions would include our right, so that's typically thought of as our trigonometric functions. I believe are classified as transcendental. We have logarithmic functions, we have exponential functions, that sort of a thing. But the inverse trig functions would certainly satisfy that description as well. So transcendental, so polynomial times transcendental, very basic. So we say, all right, cool. So that's the method that probably best describes what we have, integration by parts, product of a polynomial, and transcendental function. So then we want to remember really quickly what the setup is for integration by parts. So we usually set it up as the integral of u dv is equal to u times v minus the integral of v du. So that might not be familiar to you. You may have seen it presented slightly differently, and that's fine. We just want to be able to recognize the connection between what you may have seen in the past and what this is here. So let's perform our identification to help us understand how to implement integration by parts. So we want to, if we have u and we have dv, what we're saying is we have u, something that we can easily find the derivative of to find du, and dv, something that we can easily integrate to find v. So I can easily integrate theta, and then I can easily differentiate inverse secant. So this isn't maybe the usual substitution that we would use, or identification we would use for integration by parts, because a lot of times what you do is you differentiate the polynomial so that way it eventually goes away. But in this case, I actually want to integrate the polynomial. So I want to let u be equal to the inverse secant of theta, and that would give us du is equal to, you have to remember here, right, what's the derivative of inverse secant? So, right, I never remember that, so I go ahead and I look at my formula sheet, the derivative of the inverse secant. Let's see, I believe that's arc secant on this sheet. Arc secant is right here. U divided by absolute value, so u prime divided by absolute value, u times the square of u squared minus 1. So it's just theta in this case. So derivative of a constant is, or of something first degree is just 1. So 1 divided by theta times the square root of theta squared minus 1. So this is 1 divided by theta times the square root of theta squared minus 1. And what we're going to do here is we're going to assume theta is greater than 0, just to make things convenient, right? I don't want it to be equal to 0, because then I can't have division by 0. So it's either got to be strictly positive or strictly negative. So we're just going to assume that theta is greater than 0. So u is secant theta, inverse secant theta, du is this theta. Then dv we can identify as theta d theta, and we can integrate to find that v is 1/2 theta squared. All right, so with u and v identified, we can find that this integral is equal to u times v. So secant, inverse secant of theta times 1/2 of theta squared. So I'm going to write that as 1/2 theta squared inverse secant theta. That just looks a little bit nicer than writing the polynomial at the end. Minus the integral of v du. So 1/2 theta squared. Let's see here. Du is 1/theta square root theta squared minus 1 d theta. So we've taken our approach of integration by parts, and it has left us with this. Of course, u times v is not something that we have to worry about, right? That's integrated, that we don't have to worry about integrating that further. And this thing can be simplified a little, so I can have a cancellation and a cancellation, and I can pull out the 1/2, and that would not be a problem at all. So I'm going to simplify this just a little bit and call this 1/2 theta squared times the inverse secant theta minus the 1/2 of the integral of theta divided by the square root of theta squared minus 1 d theta. All right, so now that I'm here, what do I do next? Well, this is where we have to again ask ourselves, first, did the substitution or did the integration by parts yield an integral that is easier to evaluate? And if so, how do we evaluate this integral? So yes, I believe this is a little bit easier. It no longer involves the inverse trigonometric function. So what do we do? How do we evaluate this new integral? Well, this new integral does involve the square root of something squared minus a number squared. So this would actually suggest, right, this denominator would actually suggest trig substitution. So we've got to, if we want to do that, we think back, we look back in our notes to see, all right, when I have theta squared or variable squared minus 1, what trig substitution does that suggest? That's going to suggest a trig substitution of let's see here. Actually, it does suggest a trig substitution. This would suggest, what do we have here? Yeah, I think that would be sine let theta equals sine of, let's just call it some other variable started as theta. So let's use x. If you wanted to use phi, that would make a lot of sense. Phi is another thing that's used to represent angles. So this would work out well for us. But because the numerator is linear and in the denominator we're taking the square root of something quadratic, I want to notice that I could take a different route that is actually a little bit easier. Notice that the derivative d over d theta of theta squared minus 1 is equal to 2 theta, which is essentially what our numerator is. So I'm going to let u be equal to theta squared minus 1, and then du would be equal to 2 theta d theta. And to simplify things a little bit in our substitution, we can say 1/2 du is equal to theta d theta. Right? Divide both sides by 2 here. That gives us that this is equal to the integral of, keep the u times v that we started with, 1/2 theta squared secant inverse of theta minus d theta. Theta d theta is 1/2 du, so I'm going to pull that 1/2 out and have 1/4 integral of 1 over square root u du. Because u theta d theta is 1/2 du, so I pull the 1/2 out and I'm left with du, and this is the square root of u because I'm letting u be theta squared minus 1. So what am I trying to say here? First of all, in our decision of what technique to use, we look for obvious substitutions first. And I would actually expect you guys to think of the trig substitution first, possibly. That's what I thought of first. And then as I wanted to work through that trig substitution, I realized that I actually had an easier substitution that I could make. So I was able to do that. I was able to perform this slightly easier substitution rather than a trig substitution. Doing the u substitution, right? Integral of u to the negative 1/2 power just is an application of the power rule. So this is theta squared, secant inverse theta minus 1/4 times. I need to multiply by 1. Sorry, I need to multiply by 2 actually. 2 u to the 1/2. And then I'm going to have my plus c. So when I take the derivative, 1/2 times 2 goes away, reduced by 1, u to the negative 1/2, and that's exactly 1 over square root u. So this looks good. I substitute back, let's see here, 2 times 1/4 is 1/2, square root of theta squared minus 1, because I make my substitution back, plus c. And there we go. That is all that I am looking for. And I have evaluated the integral and written it back in terms of the variable that was given in theta. So there were 2 substitutions that we had to make. There were 2 techniques that we could use. And in fact, there were, right once we got to this new integral, there were 2 different routes that we could have taken. You could have used trig substitution as I was initially leading on to, but we actually don't have to take that route. It is a little bit simpler too, right? Check for that obvious substitution. This one, maybe not obvious, but this u substitution is definitely, I would think it's definitely easier than using the trig substitution. All right, that's it for this example. So 1 example at a time. I'll see you guys back in the workshop for another example on how do we evaluate an integral if we're not given the method, right? If we don't have a good hint as to the method. So I'll see you guys back in the workshop.